Hello all, I am Dr. Rizvi and this is our sixth video on shear force and bending moment diagram. In this video we will solve the numerical on simply supported beam carrying a UDL and a UVL simultaneously. So the lower portion in this question you can see this is UDL and it is also carrying UVL over its span. The total span of the beam is 4 meters. So let us start with the numerical. So start with the numerical. Initially we will draw the free body diagram. This is point A having a hinge support. So there will be two reactions RAY and RAX. And this is roller support. So it will be having only one reaction RB. Now there are two forces acting on the span of the beam. The total span is 4 meters. First, we will resolve UDL. The UDL will act at the center, that is 2 meters from A and 2 meters from B. And it will be 10 into 4. Here you can see that the load of UDL is given as 10 kilonewton per meter. So it will be 10 into 4, that is 40 kilonewton. This is for UDL. Now solving UVL. The total load from here to here it is 20 kilonewton and this is 10. So this height is 10 kilonewton per meter. So UVL is also of 10 kilonewton per meter and it will act at 2/3 distance from thin end, that is this much distance, 2.66 meter from A and 1.34 meters from point B, 1/3 from B and 2/3 from A, and it will be half base, that is 4 meter into height 10, it is 20 kilonewton. The total load of UVL is 20 kilonewton and total load of UDL is 40 kilonewton. This is for UVL and this is for UDL. So now we have resolved all the forces. Now we will calculate the values of reaction through general condition of equilibrium. Sigma Fx equals to 0. Therefore Rax equals to 0 since no other force is acting in along x-axis. Sigma Fy equals to 0. Ray plus Rb equals to 60 kilonewton. 40 plus 20, 60 kilonewton. And let this equation be 1. Now taking moment about point A, sigma ma equals to 0. So Ray into 0 since it is acting at point A minus ka 40 kilonewton into perpendicular distance from point A is 2 meter into 2 and minus 20 into perpendicular distance 2.66 meter and plus RB into perpendicular distance 4 equals to 0. From here we will get the value of RB as 33.3 kilonewton. We will place this value of RB in equation number 1 and we will find out the value of Ray as 26.7 kilonewton. Now we have found out the values of reaction Ray and Rb. We'll now move on to the calculation of shear force. So we just have to calculate the shear force at point A and at point B. So starting with shear force at point A, and when we cut the section here just near about point A, so it is only having one force in upward direction towards the left of the section, so it will be treated as positive and it will be equals to Ray equals to 26.7 kilonewton. Now when we are moving from point A to point B, there are three more forces, 40 kilonewton, 20 kilonewton and Rb. So we will just consider shear force just before point B. So shear force just before B, that is at this point, just before B, we will cut a section like this. So we will be having three forces, one RAY upward positive and two forces 40 and 20 kilonewton negative. So 26.7 minus 40 minus 20, and this is minus 33.3 kilonewton. Now we will find out the shear force at point B. So shear force at point B will be 26.7 minus 40 minus 20 and plus 33.3 of RB equals to 0. We have to find that the shear force at the final point must be 0. So our calculations are correct. Now for bending moment at point A and bending moment at point B, both will be equals to 0 because both are free ends. So this is not the final conclusion that our curve will be flat or it will be having no value, but it will be having some value which we will find in our question. Now we will plot these values on shear force and bending moment diagram. So we will draw the shear force and bending moment diagram. First we will draw the SFD. We know that shear force at point A is 26.7. So we will mark it as 26.7. Now shear force just before B is 33.33. So we will mark this point as minus 33.33 kilonewton. And finally at point B it is 0. This is point A and this is point B. Since we know that it is UDL and UVL combination, so we will get a parabola from A and B, between point A and B. So we'll draw a parabola here. This will be a parabola. And we'll join these points like this, straight line. This will be our shear force diagram. You know that when the shear force changes its point, at that point maximum bending moment will occur. So we will mark this point as C. Now we will draw the bending moment diagram. This is the shear force diagram SFD, and now we will draw the bending moment diagram. For bending moment diagram, we will draw a straight line. We'll mark point A and we'll mark point B. This is 0 and this is 0. We'll draw a third degree parabola here, joining point A and B, and we will drop this point here. At this point, maximum bending moment will occur. Bending moment maximum will occur, and we have to find this value. To find this value, first we have to find the intensity of UVL at this point C. So first of all, we will find the intensity of intensity of UVL at point C for maximum bending moment calculation. So we will cut this point like this and mark this point as C. The total span is 4 meters. Let this be X. The intensity of UVL at this point be Y. The total intensity is shown as 10 kilonewton per meter. Now we will find the value of Y in terms of X. So Y upon X equals to 10 upon 4. From here we can say that Y equals to 2.5 times of X. So we have find out the value of Y in terms of the distance X. Now we know that at this point C, shear force is 0. Shear force at point C is 0. So we'll now calculate the value of shear force by resolving the forces till point C, and we'll cut a section at point C. So we'll draw another diagram. Let this be point C. This is RAY. This is UVL of 10 kilonewton per meter. This distance is X and this intensity is Y. Y equals to 2.5 X. Now at this point the shear force at point C is 0 and on resolving it will be 26.7, that is RA, because it is towards the left of the section and it is in upward direction, so this is treated as positive. This UDL is downwards, so it will be minus 10 into the distance X, and for UVL it is minus Y minus 1 by 2 into Y into the distance X. From here we can place the value of Y equals to 2.5 X and we can find out the value of X. So after placing the value of 2.5, the value of X will come 2.11 meter. So we have found out the value of X and it is 2.11 meter. Now we will find out the value of maximum bending moment at this point. We'll also draw a load diagram, free body diagram for this, like this. This is RAY, 10 into X for UDL and half into Y into X for UVL. This is acting at a distance of X by 2 from both sides and UVL will act at a distance of X by 3. So to find the bending moment at point C, it will be equals to RAY into the total distance X minus 10 into X for UDL into its perpendicular distance from point C, X by 2, and minus half into Y into X into perpendicular distance X by 3. After placing the value of Y as 2.5x and placing the value of x equals to 2.11, we will get the value of bending moment at point C equals to maximum bending moment as 30.1 kilonewton meter. 30.1 kilonewton meter. We will plot this value on the bending moment diagram. This is the bending moment diagram that we have earlier obtained, bending moment diagram, and the value of maximum bending moment is 30.1 kilonewton meter. So this is how we will solve these types of questions having both UDL and UVL over the entire length of the beam. Thank you.